Greetings to all. My name is Carf Asmadin, number matrix BK25110093. Now we are going to present our project, which is called Real World Truss Analysis Project. But first, I want to introduce you our group member. Our group member is Allfhenrey Loimin, Badlisham bin Beni, Bermikarl bin Pelsikarl, Carf Asmadin, Nasrin Batrisyia, Qistina binti Nasrullah. And we are from group 2. Now we are moving on to the next part, which is introduction. I'm gonna explain to you the definition of a truss. A truss is a rigid framework of interconnected strap members that is usually from triangles. Truss was designed to support loads by distributing forces as compression or tension along the members. The purpose is to make the structure more strong, and at the same time it is lightweight. For an example, like roofs, bridges, and towers. So for our chosen structure, we chose at the Faculty Engineering near the Block C and the cafeteria.
Hello, my name is Allfhenrey Loimin and my matrix number is BK25110038. So this slide shows the photos and sketches of the selected structure, and the photo on the left shows the actual roof structure as observed on site, which helps us understand the real condition and overall shape of the design. And on the right, the sketch highlights the key measurement and the angles of the roof, including the span, height, and inclination. These sketches were drawn based on direct observation and basic measurement taken from the structure. By combining both photos and sketches, we can clearly visualize the geometry of the roof and use it as a reference for further analysis and calculation. And the next one is the free body diagram of the chosen structure. So the original roof structure is simplified into a truss system to make analysis easier, and all members are represented as straight lines connected by all the pin joints, and the joints are labeled from A to C and A to H to clearly identify each connection point. And the applied external load is shown at the top joint, while the support traction acts at both ends of the structure. And the relevant dimensions and angles are included to accurately represent the geometry of the truss. And this free body diagram allows us to apply equilibrium equation to determine the force in each member.
Hello everyone, my name is Bermikarl, and so based on our free body diagram of the entire truss, both supports at A and C are roller supports, so they provide vertical reactions only. 2 external loads are applied, 2 kN downward at the joint D and 3 kN downward at joint G. From our overall equilibrium calculations, taking moments about point A, we obtain the reaction at C as Cy, that equals to 3.25 kN. Using the vertical force equilibrium, the reaction at A was found to be Ay equals to 1.75 kN. Next, based on our free body diagrams at the joints, we identify the zero force members, which are AB, BC, BD, and FG. These members carry zero force because there is no external load at the joint and the members satisfy the zero force conditions. After that, the method of joints was applied. For all joints, member force were initially assumed to be tension at joint A, using the free body diagram and resolving force vertically and horizontally. The force member in AB was calculated using the vertical equilibrium equation. The negative result indicates that AB is in compression, while member AA is in tension. At the joint D, where a 2 kN load is applied, the free body diagram shows two unknown member forces using the vertical equilibrium equation. The force in member CD was calculated, then the horizontal equilibrium was used equation to determine the force member in DE. At joint E, there is no external load. Using equilibrium equations and the non-force from adjacent joints, the force in member EF was determined. At joint G, a 3 kN downward load is applied, and based on the free body diagram, the vertical equilibrium equation was used to calculate the force member in EG and GH, while member FG is a zero force member.
Greetings to everyone. My name is Badlisham bin Beni with the number matrix of BK25110319, and I will explain the summary of member force obtained from the Truss analysis. So this table shows each truss member, the magnitude of force acting on it in kilonewtons, and whether the member is in tension, compression, or a zero force condition. Starting with members under tension, we can see that member AA carries a tensile force of 3.03 kN, while member DE carries 0.73 kN in tension. The highest tension force occurs in member GH with a value of 5.2 kN, indicating that this member is being pulled significantly. Next, for members under compression, member AB experiences 3.5 kN, DC and EF each carry 2.13 kN, and EG carries the highest compressive force of 6 kN. This suggests that EG is a critical member resisting compressive loads and is more prone to buckling if not properly designed. Lastly, members AB, BC, BD, and FG are identified as zero force members, meaning they carry no internal force under the given loading conditions. However, these members are still important as they help maintain the overall stability and geometry of the truss. In conclusion, this summary helped us identify critical members under high tension and compression, as well as zero force member, which is essential for efficient and safe structural design.
Hi, my name is Nasrin and I will be presenting about the discussion. So this slide shows the discussion of results, focusing on the geometry and configuration of the truss structure. The structure analyzed in this project is a real world roof truss, which was examined using Statik's principles. To simplify the analysis, the truss has a symmetrical configuration with a total span of approximately 2.6 meters. Upper chord members are inclined at angles of about 30 degrees and 70 degrees, while the bottom chord remains horizontal. This simplified model allows the internal forces in the truss members to be analyzed effectively while still representing the actual behavior of the real structure. Okay, so as you can see that there's a figure show a simplified two-dimensional model of the truss showing joints, which is A and C, members A, B, C, D, E, F, G, and H, dimension, and applied loads. Okay, now let's look at supports, loads, and equilibrium results. So this slide presents the supports, applied loads, and equilibrium results for the truss. The structure is supported at two joints providing vertical reaction forces only. Since there are no horizontal external loads, the horizontal reaction are assumed to be zero. Two vertical loads of 2 kilonewtons and 3 kilonewtons were applied at selected joints, giving a total applied load of 5 kilonewton. So by using static equilibrium, the support reaction will calculate as 1.75 kilonewtons at support A and 3.25 kilonewton at support C. This value satisfy equilibrium, confirming that the structure is stable. Okay, now let's look at internal forces analysis and key member force results. So this slide presents the internal force analysis of the truss using the method of joint. The analysis began at joints with known reaction forces, allowing several zero force members to be identified, namely members AB, BC, BD, and FG. At joint A, member AB carries a compressive force of 3.5 kilonewtons, while the bottom chord member AA is in tension with a force of 3.03 kilonewtons. At joint D, member CD experiences a compressive force of 2.13 kilonewtons, while member DE carries a tensile force of 0.73 kilonewtons. At joint G, the applied load results in member EG carrying a compressive force of 6 kilonewtons, while member GH is in tension with a force of 5.2 kilonewtons. Overall, the results show that the upper and inclined members mainly carry compression, while the bottom chord members carry tension, which is consistent with typical truss behavior. Okay, lastly, let's look at assumptions and limitations. For this analysis, several assumptions were made to simplify the truss behavior. First, all joints were assumed to be pin-jointed, meaning no moments are transferred between members. Second, loads were applied only at the joints, and the self-weight of members was neglected to focus on axial forces. The structure was analyzed as a two-dimensional static system, assuming equilibrium under applied loads. In terms of limitation, real structures may not have perfectly pinned joints, and environmental loads such as wind were not considered. Additionally, the dimensions and load values were estimated, which may differ from actual condition. Despite this limitation, the assumptions are reasonable for academic analysis and effectively demonstrate the application of static principle to a real-world truss. Thank you.
In conclusion, structures like towers, bridges, roof, and any other engineering structures that we have seen, it is actually the members of the truss that uses triangular arrangements to distribute forces, has compression and tension in it. Therefore, the truss provides high strength, stability, and material efficiency that makes the structure is safe. That's all from Group 2. Thanks.